Having constructed a square wave, so a function that, or an external force that turns on for 2 seconds, and then is off for 2 seconds, and then is on, and so forth here, what we're going to do is study the effect of applying that on-off force, which has exactly the same period as the natural oscillations of the system here. Taking the Laplace transform of the differential equation, and we're going to start at equilibrium. We're going to end up with s squared y of s minus sy of 0 minus y prime of 0 plus pi squared over 4 y of s, and that's going to equal the transform of the right-hand side. So the Laplace of f naught times that square wave. We computed that earlier, so we'll just copy this down as it stands. We had two coefficients for y of s, the s squared and the pi over 4. We're going to start at equilibrium, so both of these other values, initial values, are 0. And then the transform of this right-hand side would be f naught times e to the minus 0s over s minus e to the minus 2s over s, alternating signs, plus, minus, plus, e to the minus 4s over s. And that's just capturing the step functions that give us the on-off motion we're looking for. We can now solve for y of s. It's fairly straightforward. And we get 1 over s squared plus pi squared over 4 times f naught. So we'll put an f naught here. And we have our e to the minus 0 s's and so on. Our next challenge is to group things a little bit differently. We're going to put the f naught all the way out front, and then we have e to the minus 0s minus e to the minus 2s plus e to the minus 4s minus e to the minus 6s, and so on, times 1 over s times s squared plus pi squared over 4. This part here is ripe for partial fractions. Everything else can be left alone for the moment, so we'll continue this on the next page. Focusing our attention on the rational function here, we would break this down into its component parts with partial fractions. We won't show all the work here, but we end up with 4 over pi squared times the 1 over s term minus 4 over pi squared times s over s squared plus pi squared over 4. What that means for a y of s, which is equal to f naught times the set of exponentials in alternating signs, is this portion of the function has not changed. However, we're then multiplying it by this transformed or partial fraction decomposition form, which is a little hairy looking except for, or only in the constants, the actual transform itself is quite straightforward. We recognize that this is the transform of a constant, and this is the transform of cosine. So now we're actually ready to do the inverse. And what do we get? We get f naught. We actually have a common 4 over pi squared. Let's bring that out as well. Then we have the infinite series of step functions here, each one which is combined with the 1 over s and the transform of cosine here. So we'll just go term by term. The e to the negative 0s times 1, well, e to the negative 0s is just 1 itself, so we just get the transform of 1 over s, which is the constant 1. Then we have minus cos of pi over 2 times t, the transform of the second term with this already brought out front. We had the next step function, so minus u2 times the transform of the constant function 1 minus the transform of the cosine, cos of pi over 2, but the t is shifted by t minus 2 due to this step function, due to this negative exponential of e to the negative 2s. And then we're going to have plus u4, 1 minus the cosine of pi over 2 t minus 4, and so on. Now we can see the series, we can see the pattern that's going to emerge, 1 minus a cosine function. What's going to make this sum manageable to deal with is the fact that this cosine, which is shifted by 2, is shifted by half a period. The period is 4, and we've only shifted it by 2. That's going to equal negative cos pi over 2t, with a negative out front, so we could rewrite this entire term here as 1 minus cos pi over 2t. This term, where the shift is by 4, is going to be equal to 1 minus exactly what it started with, pi over 2t, because we've shifted it by 1 full cycle. The real payoff, where we can see the structure, is if we write this in piecewise format. On the first interval, from 0 to t to 2, on that interval there, the only function that's active is the 1 minus cos pi over 2t. All these other functions get turned on at time 2 or time 4, time 6, and so on. On the next interval, we had that function on, and then we also have the u2 function that turns on, so we get these elements as well. And by the time we accumulate everything in there, we're going to subtract a 1 plus cos of pi over 2t, and that's going to be between 2 and 4 for time. But that cancels the 1, and we end up with negative 2 cos pi over 2t on the same interval. Well, hey, we had negative cos, now we have negative 2 cos. If we are careful with our third case, where we add the u4 in, we're going to be subtracting yet another cosine, cos of pi over 2t's, and that's going to be from 4 to 6. And keeping the pattern going, if we went from 6 to 8 seconds, we would have minus 4 cosine pi over 2t's. With all that structure now, we can see that we have 1 cos in the first interval, negative 2 coses in the next, negative 3 in the third, negative 4 in the last, and that describes linearly growing amplitudes of oscillation. So in fact, we do have something with the same effect of resonance here. Even though our stimulating function was not a sine wave, because we used the square wave with the same frequency as the natural oscillations or the unforced oscillations, that leads to effectively the same result of resonance and linearly growing amplitudes.